All right, get ready to dive into a world that literally glows in the dark. It's radioluminescence. We're going to be talking about how things can emit light, without needing to be plugged in.
It's a question that's fascinated people for a long time. I mean, who hasn't looked at a in the dark watch and wondered how it works, right?
Yeah, so radioluminescence is all about using radioactivity to make light. But is that uh, dangerous? I mean, the word radioactive is a bit, you know.
It can be, yeah. But the thing is, it's all about context. Like with many things in science, we need to understand how radioluminescence works, and the first step is to separate it from something you're probably already familiar with, phosphorescence.
Oh, right, like those glow-in-the-dark stars people put on their ceiling?
Exactly. Those use phosphorescence, where they absorb light and release it slowly. It's kind of like charging up a battery and letting it drain slowly. But with radioluminescence, there's no need to charge it up first. The light it gives off is continuous, and it's all powered by the decay of radioactive isotopes.
No batteries, no need for light exposure. It just glows on its own. That's pretty cool.
It is, and a great example of this is something we see all the time, those green exit signs.
Hold on, you're saying those exit signs are radioactive?
Many of them are. They use tritium, which is a radioactive form of hydrogen. When tritium decays, it releases beta particles, which are basically really fast electrons.
So tiny electrons flying around. How does that make light?
Well, that's where phosphors come into play. These special materials, often mixed with the radioactive substance, are energized by those beta particles. That energy then gets released as light.
So the phosphors are like little light bulbs, switched on by those beta particles from the tritium.
Yeah, you could say that. And since tritium decays slowly, it has a long half-life, meaning those signs can glow for over a decade without any external power.
Amazing. But it's safe, right? I wouldn't want a dangerous radioactive sign hanging over my head.
That's a good point. And it leads us to a darker period in the history of radioluminescence, radium paint.
Oh yeah, the radium girls. A tragic story about the early days of using radioactivity. Those glowing dials on old watches, right?
Exactly. Before we understood the dangers, radium, which is a much stronger radioactive element than tritium, was used in the paint for those things.
And those factory workers, mostly women, who painted those dials, they really suffered because of it?
Sadly, yes. They used to lick their paintbrushes to get a fine point, accidentally ingesting radium along with the radioactive phosphors.
That's awful.
It was a turning point, though. It led to stricter safety rules and a better understanding of how to handle radioactive materials. And it shows a big difference between the types of radiation. Tritium mainly emits low-energy beta particles that can be stopped by a piece of paper. Radium, however, emits alpha particles, which are much more harmful and can cause serious damage if they get inside the body.
A good reminder that while radioluminescence is cool, we need to be careful with the materials involved.
Absolutely, and it highlights how important those phosphors are. They're what turn the invisible energy of radiation into the light we can see.
So tell me more about these phosphors. They get excited by the radiation, but why do they glow in different colors? I mean, exit signs are usually green, but I've seen other things that glow in different colors.
You're right, it's the type of phosphor that determines the color. Different phosphors have different energy levels, and when those energy levels change because of the radiation, they release that energy as light, and those different energy levels correspond to different colors.
So, like the phosphor is a translator. It takes the language of radiation and turns it into the language of light.
That's a great way to put it. And scientists have all sorts of phosphors, so they can make radioluminescent materials that glow in all sorts of colors, from green and blue to orange and red.
That's awesome. It's like a palette of glowing colors. So, besides exit signs, where else do we find radioluminescence being used today?
One area where it really stands out is the military.
Really? Tell me more. This sounds interesting.
Think about a soldier who needs to aim in the dark. They can't use a flashlight, right? It would give away their position.
Yeah, that makes sense. So, how does radioluminescence help?
This is where tritium's safety and long lifespan are really useful. And any amounts of tritium sealed up safely are used in gun sights, so soldiers can see their target without needing a separate light source.
So, the sights themselves glow in the dark, powered by the tritium. That's really clever.
It is, and it's not just gun sights. You can find it in compasses, airplane instruments, even markings on equipment. So things can be seen in low light without needing batteries or other power.
Wow, so radioluminescence, even if people don't always think about it, is used in some pretty important situations.
Definitely. And I think this is a good time to switch gears and talk about something that often gets mixed up with radioluminescence, bioluminescence.
Ah, yes, the amazing world of creatures that make their own light, like fireflies or those deep-sea fish that look like they're from another planet. But before we get into that, maybe we should do a quick recap of what we've covered so far.
Sounds good. Let's make sure we're all on the same gleaming page, so to speak. So we've talked about radioluminescence, how it uses radioactive decay to make light, and how it's different from phosphorescence.
And of course, we talked about tritium, that radioactive isotope that's in those exit signs we see all the time.
Right, those signs are a good example of how we can use radioluminescence safely and for a practical purpose. And then we got into that darker part of its history with the radium girls.
Yeah, their story is a reminder that safety is important, and we need to understand the risks involved with radiation, especially different types of radiation. It also showed how important those phosphors are in the whole process.
Definitely. They're the link between radiation, which we can't see, and the light that we can see. They take the energy from radioactive decay and turn it into those glows we see. We even talked about how different phosphors make different colors, so there are a lot of possibilities for how radioluminescence can be used.
And right before we took a break, we were about to talk about bioluminescence, which is pretty cool. Nature has its own ways of making light, huh?
Absolutely. Radioluminescence uses radioactive isotopes, but bioluminescence is all about chemistry. It's a chemical reaction that happens inside a living organism.
Okay, break that down a bit. What kind of chemical reaction are we talking about?
Well, imagine a molecule called luciferins. When it reacts with oxygen, with the help of an enzyme called luciferase, they release energy as light.
Luciferin? Luciferase. Those names sound kind of mythical.
They do, right? And bioluminescence has always felt a bit magical to us. Like, think about fireflies on a summer night, or those creatures in the deep ocean that glow.
It's like nature's own light show. But if it's a chemical reaction, does that mean the light eventually stops? Unlike radioluminescence, which glows continuously.
That's right, bioluminescence is temporary. The light fades as the luciferin is used up in the reaction. But some organisms can make more luciferin, so they can glow again and again. Fireflies, for instance, flash their lights to attract mates. Some deep-sea creatures use it for camouflage, to defend themselves, or even to attract prey.
So even though they work differently, both radioluminescence and bioluminescence have their own purposes. And they're great examples of how light is used in nature.
Exactly. And just like with radioluminescence, humans have been inspired by bioluminescence to try and use it in different ways.
Oh, really? Like what? Are we talking about like glowing plants to replace streetlights?
Well, that's one idea, and scientists are working on it, but there are other really interesting ways we're using bioluminescence, like bioluminescent imaging, where researchers use luciferase to track cells and see biological processes happening in real time. It's like having tiny lights inside living things, showing us what's going on at a microscopic level.
That sounds super useful for medical research. Are there any other examples?
Yeah, a bunch. Scientists are experimenting with using bioluminescent bacteria to find pollutants in water. They're even looking at using them as a source of sustainable lighting. Imagine cities lit up by bioluminescent trees. Wouldn't that be cool?
That's an amazing image. Glowing trees, bioluminescent plants. It'd be like living in a fantasy world. But wait, what about those glow-in-the-dark toys and stickers we used to play with? Was that bioluminescence too?
Good question, but that's actually a common misunderstanding. Those things use phosphorescence, which is what we talked about earlier, the stuff that absorbs light and then slowly releases it, like it's soaking up light and then letting it drip out as a glow.
Oh, right, like a light battery. So we have radioluminescence, bioluminescence, and phosphorescence. 3 different ways things can make light. It's amazing how many light shows are happening around us all the time, both in nature and because of things humans have created.
It really shows how creative and diverse the universe is, both in its natural forms and in how we try to understand and use it.
This whole conversation has definitely changed how I see the world, like literally. But before we get too carried away, maybe another recap is in order. We've talked about radium dials and glowing plants, and I just want to make sure we're all still on the same page.
Good idea. A recap will help make sure we haven't missed any of the glowing details.
Okay, so first we revisited the differences between radioluminescence, bioluminescence, and phosphorescence, and how they work and what they're used for.
Then we talked about how humans have used these different ways of making light.
Yeah, we talked about the radium girls, how tritium is used by the military, and how exciting it is to think about bioluminescent imaging and glowing plants.
And right before this recap, we made it clear that those glow-in-the-dark toys and stickers from our childhoods use phosphorescence, not bioluminescence.
It's been a pretty illuminating journey so far.
It has. And speaking of illuminating journeys, you know what else is pretty interesting? The way we're using phosphorescence, that simple glow-in-the-dark effect, to create some really incredible technology.
Really? Tell me more, I'm all ears.
Well, picture this. You're driving down the highway at night, but instead of streetlights or your headlights, it's the road itself that's lighting your way.
Wait, are you talking about glow-in-the-dark roads? That sounds like something out of a movie.
It might sound futuristic, but it's actually starting to happen. Scientists are developing glow-in-the-dark road markings using phosphorescent materials. They absorb sunlight during the day and then release it as light at night. This makes it easier for drivers to see, especially in areas with few or no streetlights.
That's amazing. It look really cool. And it could make roads safer, too. Are there any other ways we're using phosphorescence like this?
Absolutely. Researchers are looking into using it in all kinds of things, like emergency signs that would glow in the dark if the power goes out, or even clothes that light up on their own.
Clothes that light up. You mean like glow-in-the-dark clothing?
Exactly. Think of the possibilities for safety, fashion, even art.
I can already imagine glow-in-the-dark fashion shows and art installations, so it sounds like phosphorescence is moving beyond toys and stickers and becoming something really innovative.
Definitely. It's a great example of how something we might have thought was just a fun little thing can be turned into cutting-edge technology with the potential to change the world.
This deep dive has really shown how interesting and diverse the world of luminescence is. From the dangers of radium to the possibility of glowing trees, we've learned a lot. Before we finish up, maybe one last recap to tie it all together.
Okay, let's shine a light on the key points one last time.
We started by looking at the differences between radioluminescence, bioluminescence, and phosphorescence, how they work and how they're used.
Right. Then we talked about the amazing ways humans have figured out how to use these different ways of making light.
From the story of radium girls to the military using tritium to the potential of glowing plants, we've seen how these different forms of luminescence have impacted our world.
And we finished up by seeing how phosphorescence is going beyond just being a novelty and becoming a really advanced technology.
Yeah, from glowing road markings to clothes that light up on their own, the future of phosphorescence looks really bright.
This deep dive has really opened up a world of glowing possibilities.
It sure has. But before we go, I have one last thought for our listeners. We've talked about light coming from objects, but what about light coming from inside us?
That's an interesting idea. What do you mean?
What if we could use bioluminescence to create a world where our bodies actually emit light? Not as a medical thing, but as a way of expressing ourselves. Imagine if we could see each other's emotions through subtle changes in our bioluminescent glow.
A world where happiness would look like a bright aura and sadness would be a soft, dim glow. That's a beautiful and thought-provoking idea.
It is, isn't it? A world where light becomes a language, not spoken with words, but with our very being.
A world where our inner light shines as bright as the world around us.
And with that beautiful thought, we wrap up our deep dive into the fascinating world of luminescence. Until next time, keep exploring and learning, and keep letting your own light shine. It really is. It makes you think, doesn't it? But before we wander off into the philosophical, you mentioned glowing plants. How close are we to actually seeing those?
It's a question that gets people excited, and for good reason. We don't have bioluminescent trees lining our streets just yet, but scientists have made some pretty big steps.
So glowing plants aren't just science fiction anymore.
Not at all. Researchers have put the gene for bioluminescence into different kinds of plants. There are already plants, like right now, in labs that give off their own light.
That's amazing. But are there still challenges before we see them lighting up our homes?
Of course. One of the biggest ones is making the light brighter and last longer. Right now, the glow from these genetically modified plants is still pretty faint, compared to a regular light bulb.
Makes sense. So what affects how bright a plant glows?
It comes down to, well, how well that luciferase enzyme works inside the plant's cells. Remember, it's that reaction between luciferin and oxygen helps along luciferase that creates the light. Making that reaction work smoothly in a plant cell, that's complicated.
Sounds like a delicate process. But if scientists figure it out, what are the benefits of glowing plants? Could those glowing trees replace streetlights like you mentioned?
A lot of researchers are hoping for exactly that. Think about it. Cities lit up by, the soft glow of trees, using less energy and creating less light pollution.
That would be incredible. And good for the environment.
Right. And think about places that don't have reliable electricity. Glowing plants could give them a source of light that's sustainable and affordable, really changing people's lives.
That's an inspiring thought. Makes you wonder, when did people first get fascinated by things that glow?
Our fascination with luminescence, it goes way back, centuries, even thousands of years. Long before we knew the science, our ancestors were amazed by fireflies, glowing fungi, even the moon and stars.
It's easy to imagine how those natural light shows must have seemed magical, almost supernatural back then.
Yeah, I bet. Those experiences probably sparked our curiosity about light and how it works. We went from simple handles to inventing the light bulb, always trying to understand and control light.
And that search is still going on, with scientists pushing the boundaries of what's possible with radioluminescence, bioluminescence, and phosphorescence.
It shows how fascinated we are by light, its beauty, how mysterious it can be, and how it can literally illuminate our world, but also help us understand it better.
This whole deep dive has been really eye-opening, literally. It's made me appreciate light in a whole new way, not just for seeing, but as something that's part of like everything in the universe, from the smallest atoms to, well, to the entire galaxy.
Yeah, it's like a reminder that even in the darkest times, there's always light to be found, both in the real world and, well, metaphorically.
Well said. And on that note, we're going to wrap up this episode of the Deep Dive. We've explored the science, the history, and, well, the possibilities of luminescence. It's something that still, amazes us and gives us new ideas. So until next time, keep exploring, keep learning, and keep letting your own light shine. 6TR.